Ladies and gentlemen, please welcome Senior Vice President, Business Strategy and Marketing for Autodesk, Lisa Campbell.
Good morning. I see everybody survived last night's party. So welcome to day 3 of the main stage presentations. We have an exciting morning for you planned. So design and manufacturing is changing at a rapid pace. I think, by the way, that this is the best time to be in this industry because we're at the cusp of something truly remarkable, and that is the convergence of design and manufacturing. Now, 2 days ago, you heard Andrew talk about more, better, and less. And what was the key theme about what's driving that? Automation. And I would say that automation is good. And why is automation good? And I would give you 3 reasons why it's good. Number 1, it frees up our imaginations to be more creative and more innovative. The second reason is it frees us up from the constraints of the manual manufacturing process. And third, it augments our natural human capabilities. So just as an example, how many people in here have an iPhone or a smartphone? Like, everybody's like, I have 3. Now, when's the last time you had to remember facts and figures? You don't, because you're already augmented with automation, because all of us just ask Siri or we Google it. And how about, when was the last time any of you had to turn on a radio station and tune it? Because we just ask Amazon Alexa and we say, play something from Spotify or Pandora, right? And how many of you have children? It augments our children's natural capabilities to do homework. How many of you have a child that says, hey, Alexa, what's the tallest mountain in the world? It helps her do their homework. And how many of you have a Fitbit or a smartwatch? This is a very well-automated group. When's the last time you had to manually enter any information about your physical activities? You don't have to do that anymore because your Fitbit just tracks it. In fact, I have found that the Fitbit, it nags you. You're sitting for too long. Get up, you gotta move around. You don't have enough steps. You haven't hit 10,000 steps today. So I'm talking about this kind of automation, but even more powerful for design and manufacturing. And that's why I think this is the best time in the world to be in this industry. All right, so take our good friend, the milling machine. How many of you remember the days of using this? All right, lots of people. Somebody, when I was talking to them about this photograph, they said, you know, you can actually smell the grease just by looking at this picture. Now, I'm sure some of you are still using it. And it's a fabulous machine, but the problem is that it constrains what we can physically make. You can take a square block, and you can cut the corners off, but at the end of the day, it's still a square block. And our imaginations are much better than that. We can imagine much bigger things. Now, I'm not talking about automating the operator of this machine. I'm talking about something completely different. I'm talking about empowering humans to do what we are great at, to be more creative and more innovative so that we're actually programming machines like this to manufacture goods that we couldn't do in a manual way. Now take a look at this amazing bridge. In fact, I was in Amsterdam a couple of weeks ago and I wasn't sure if this was going to be implemented yet, and it wasn't, because I would have thought this would have been amazing. So this bridge is being built by MX3D. And it's 3D printed in steel. And this is going to span a beautiful canal in Amsterdam. Now, I bet you many of us say, I could have imagined something amazing like this, but there's not one person here, including myself, that could have produced this without automation. What did MX3D do? They actually used and transformed with intelligent software a robot and a welding machine and created a large-scale 3D printer that was able to 3D print this in steel, a pedestrian bridge in steel. And what's even more amazing about this is that they were able to do this with less material. And take a look at this picture. With this kind of automation, they're able to create highly custom organic forms. And the true beauty of this is with automation in design and manufacturing, you could do bridges like this that are all of them that are unique and different and customized. How about a different example? Under Armour. Now, Under Armour has fully embraced the convergence of design and manufacturing, and they've only been able to do this because of automation. Now, take a look at the sole of this shoe. That lattice work is so complicated, there's not one of us that could have designed and modeled this without generative design. We needed a computer to do it. And take a look at that manufacturing process. That complex lattice work, we could not have done that without advanced manufacturing capabilities like 3D additive printing. And because they fully embrace that, you can make unique soles like this. Now, I want to talk to you about a completely different industry, the maritime industry. Now, the Port of Rotterdam wanted to fundamentally change what happens in their port. They can actually lose hundreds of thousands of dollars a day if a ship cannot get in and out of port. And what they said they wanted to do was solve the problem of being able to manufacture at the point of demand. So they built a manufacturing facility, Ram Lab, and within that facility, they were able to use a 6-axis robot and high-rate deposition of metal to create this beautiful propeller that you see them creating. Now, I understand that this propeller was just installed in the ship last week, and this ship will be leaving port in the next week or so. So imagine being able to do something like that, where you get this amazing, and think of the scale, the build envelope for that propeller. They want to bring this kind of manufacturing at the point of demand to other industries. Imagine what this would be like in transportation, in space, or in the oil and gas industry. Now take a look at this warehouse, filled to the brim with spare parts. Now, how many of you heard Andrew the other day on stage say, there's 30% waste in construction? You remember that when he was showing the landfills? Now, I bet all of us in this room were like, well, that kind of waste would never happen in the design and manufacturing space. Well, 70% of spare parts around the world are wasted. Think about that. 70% of spare parts are wasted. Now, imagine if you brought this process that Port of Rotterdam did with Ram Lab, where you could manufacture at the point of demand. You build what you need, where you need it, when you need it. You would essentially be using 100% of your inventory. Imagine the change in the world if we could do that. Now, the amazing thing here is automation is good, right? It frees up our creativity. It frees us up to be more innovative. It frees us up from the constraints of the manufacturing process, and it augments our natural capabilities. And the really great news is I'm not talking about technology that you have to wait 5 or 10 years to get. All of you have the ability to get access to this good automation now. And who better to explain that to you than our own Stephen Hooper, who's the Senior Director of Business Strategy and Marketing for Design and Manufacturing. Thank you.
Amazing. That was awesome. Thanks, Lisa. It's great. It's also great to see all of you here today, especially given the party last night that I had to sit out on the bench. It's a painful process. So Lisa started this morning by talking about automation and why it's good. But what I want to do is I want to talk to you about why automation isn't just good. I want to continue that discussion and explain why automation represents opportunity, tremendous opportunity for everybody in this room. Not only because it unlocks our creative potential and freedom to develop things, but because it lowers the barrier to access of new opportunity for all of us. Now, when I trained as a mechanical engineer, it was on the understanding that when I finished and graduated, I would go to work for somebody else for the next 40 years, for 5 days a week, 9 hours a day, helping take somebody else's ideas to market. But our world's changing. The tools and technologies that we now have access to mean that for many of us, we'll get to experience many different disciplines throughout the course of our career. And for some of us, we'll get the opportunity to go and pursue our own goals and ambitions and start our own businesses in ways that were never before possible. Now, I want to illustrate what that means, both in terms of impact to our industry, as well as the tools and technology that we deliver to you. And to do that, I want to talk about my favorite thing: customers, you, and the amazing work that you produce. And I'm going to use that to highlight some of the announcements we want to make this morning, as well as helping you understand more about our strategy and direction in the design and manufacturing market. So take, for example, Modbot. Modbot are a small startup company based in San Francisco, and they're radically redefining robotics. Now, Adam, who's the leader of this organization, and his team are making modular robotics accessible to everyone. Now, this is a tremendous challenge for them. They've had 6 different disciplines that they've had to embrace as part of the product development and manufacturing process, organized across 6 different geographic locations. And they managed to get to the first prototype that you see on the screen behind me in just 6 months. And what they're doing is they're redefining the world of robotics and modular 6-axis robotics, making it accessible to all of us. And in doing so, they're helping redefine production technology. For just $15,000, you can get access now to a modular 6-axis robot, so that the automation you heard Andrew talk about during his keynote presentation on Tuesday morning is now accessible to all of us. And we can all start to embrace these new forms of automation technology. And that means that the nature of production itself is changing radically. Automation is starting to affect every aspect of physical manufacture, and that even includes construction. So Lisa mentioned the huge amounts of wastage that you see out on a construction site. You, everyone in this room, have the opportunity to redefine that. There are a couple of thousand people in a room just down the hall from here who could use all of our help. And that represents an opportunity for you in a new market space to start developing products to help automate other aspects in other industries. But it's not just robotics that are automating the production process. 3D printing is also poised to redefine the manufacturing process. Take, for example, Under Armour. This is the shoe that Lisa just mentioned. It's the Under Armour Futurist Architect shoe. The lattice in the sole of this shoe is the perfect example of why we can no longer separate design from manufacturing. As engineers, we're taught some fundamental guiding principles. One of those principles is that complexity equals cost. The introduction of any manufacturing process to modify the raw materials that you choose to manufacture your product traditionally means that you're introducing manufacturing cost into the process. In essence, the very presence of any air or hole in that product represents manufacturing cost that you're introducing to the process. But 3D printing turns that logic on its head. In the world of 3D printing, there is no cost for construction. There is no cost for complexity. Air pockets within design are free because essentially you're paying just to lay the material. So the inverse is true. It costs you money to lay down material, so that the more intricate the design becomes, actually you're saving money because you're not paying to produce that material. Now, you can't embrace that ideology unless you radically rethink the way that you design and manufacture. Not as 2 separate processes, not as design with CAD and manufacturing with CAM or simulation. You need to redefine these processes as one single process. So to illustrate that point, what I want to do is just take a step back and look at an example from a different industry. So I'm going to pause for a moment and just consider the film and media industry. And let's step back to the 1990s and think about Toy Story. So the example you see behind me on the left is Woody from Toy Story. Now, Woody is completely manually modeled. Everything about Woody was developed by a 3D artist working in a 3D modeling environment, right down to the spurs on his boot that had to be manually produced by an artist and then animated. Now, step forward in time to the 2000s and think about Monsters, Inc. and Sully. Now, Sully also employs some manual modeling, but there's no possible way that a modeler could have sat down and produced all the intricate fur and made it behave in the way that's lifelike. You would have needed some form of automation to do that. And that's why the fur on Sully is procedurally produced by a computer algorithm that automates the process of defining that fur and simulates its behavior, understanding the environmental conditions that Sully is in. And this is no different to what we're doing in the design and manufacturing market. So take, for example, this cylinder head from a well-known automotive manufacturer. Parametrics, which were a tool invented back in the 90s and made accessible to everyone, are still a great tool for doing things like defining the mounting locations, the ports, and the valves. But when you take a look at the intricacy of the lattice structure in what would have traditionally been a solid casting, you can see that no human being would have been able to have sat down and modeled that degree of intricacy. And if they had, they would have wasted a tremendous amount of time. You'll also notice that that lattice isn't uniform in structure. It's variational. And the reason that it's variational is that this isn't just topology or 3D models that have been built in isolation. It's been done iteratively with simulation to understand the performance characteristics of this cylinder head. So not only does the lattice lightweight the cylinder head, it also acts as a heat sink, dissipating heat, because we've iteratively embedded simulation as part of the product development process so that we can optimize the lattice, not only to withstand its structural loading conditions, but also to dissipate heat so that we can run the engine at a higher temperature, a higher pressure, and get better vehicle performance in race conditions. And the question I would ask you is, what would happen if you were a producer of traditional cast-based designs as a subcontractor for another client, and somebody else started a business where they were able to create this type of design in 3D print, and every design can be unique and customized to the precise requirements of the end customer? The answer to that question is that they'd probably put you out of business overnight. It would create a tremendous amount of disruption. And that's exactly what we want to help everyone prepare for. And so to do that, we've worked with some key customers. Take, for example, Airbus. Now, we've been working with Airbus on a research project. I want to explain a little bit about that research project, and then later on, we're going to show you how you will be getting access to this technology through the subscriptions that you all have access to. Now, Airbus have a corporate initiative to reduce the amount of CO2 emissions by 50% by 2050. That's their strategic intent, their long-term objective. But to get to your long-term objective, you have to go through a process of strategic realization. And that realization means taking some of those lofty goals and making your first steps towards them. And so to do that, Airbus have worked on what they call a Bionic partition. Now, to give you some context for this Bionic partition, it sits at the rear of the aircraft, and it's where the cabin crew's jump seats are located for takeoff and landing. So it's representative of a real piece of aircraft equipment that has to withstand rigorous FAA legislative testing, up to 16 Gs, and then it has to be flight tested and put into action in full-service aircraft. It gives Airbus the optimum opportunity to test this technology, refine it, and develop it so that they can pursue that long-term strategic intent. Now, to do this, they've had to radically rethink the way that they ideate designs. Now, as a mechanical engineer, most of us would probably start with some initial conceptual design, some idea. And being good engineers, you'd probably iterate a few times on that. You might look at several solutions in the local solution domain. The problem is that with a design as complex as this, even if there were only, say, 15 variables, and each variable had maybe 10 possible parameters, you would end up with a potential solution domain of 10 to the power of 15 possible alternatives, a solution domain far too big for any individual human being to explore mentally. And that's where some of the augmentation that Lisa spoke about in her opening can be employed here to help a mechanical design engineer fully explore this solution domain. And this represents just a small sample set. There's a potential of 100 million different solutions. So using the power of the cloud, what we've been able to do is combine topology definition with simulation and manufacturing process to iteratively solve for not one right solution, but 100 million different potential solutions. What you see here is a tool that we've developed with Airbus to help engineers explore the solution domain. They can look at a sample set of 36,000 different potential solutions and pivot things like force against displacement or displacement against material or material versus manufacturing process. Because in this scenario, there isn't just one right answer, there are many viable possible alternatives. And what this tool does is it doesn't replace the design engineer, it augments them with the ability to explore that entire solution universe so that they can start to do what a human being's good at. They can start to look at the creative process of making trade-off decisions on requirements and how best to meet their customers' needs. And in this case, you can see there's 10 different solutions that might meet the criteria of the customer. And the design engineer can now use that information to make a more informed decision about which design strategy to pursue. But just for a moment, I want you to forget that we're talking about topology and imagine that that lattice structure that you see there is laid flat. And think that that lattice structure might actually represent the flow of material through a factory. And if you think of that, you'll then realize the potential impact and the limitless possibilities for generative technology, not only in design, but across the whole of the design and manufacturing process. And that's what we're working on as an organization to help augment you across the whole of the design and manufacturing process. Now, in doing that, we're creating a lot of data. That data gets created at different points during this process. There's a tremendous amount of data that gets created by the product itself. So I wanted to use a slightly different example here from a customer called Door. Now, Door make a sensor that sits at the top of a doorway in a retail establishment, and it tracks people coming in and out of a store. And what I want you to think about here is how would Door have traditionally differentiated themselves in a product development market? They'd have probably looked at the functional performance of the product, of its cost, of its quality, and if they weren't careful, if they encountered a number of competitors, they'd probably end up in the better, faster, cheaper cycle towards a commodity product. But that's where Door has chosen a different path, because they're embracing connectivity to the cloud as part of the product development process, but also in an effort to help customers gain more insight. Because when they track people coming into stores, they transmit that data to their cloud service, which cross-references it with things like weather, local sports activities, games that are going on in the surrounding area. And using that information with machine learning, they can derive insight, predictive insight that helps store owners understand the likely impact ahead of time so that they can bring people in and staff up the store. And as you can see, the physical product itself, although very beautiful in its style, is not the core differentiator. The core competitive separator for Door is their ability to connect data in the cloud and provide insight as a service. So they've actually transitioned from product to product as a service. That's one illustration of where information can provide insight, but we also gather information during the manufacturing process itself. In this example from machineering, what we're doing is gathering information from machine tools on the shop floor and then using our Forge services to create a virtual reality environment in which customers can produce virtual commissioning studies. Now, in this example, for this particular customer, the commissioning of a plant traditionally takes about 2 weeks. That's 2 weeks of lost productivity of capital plant assets that total more than $100 million. With virtual commissioning, their production engineers can start to commission the plant before any foundation is even laid. It doesn't eliminate the need for physical commissioning. What it does is it reduces the time by 50%. It gets their operational plant effective, productive, 50% faster. And that's a huge return on investment when you consider $100 million worth of capital plant equipment. So this is another excellent example of where data can be brought together to start to augment the human being and automate the design and manufacturing process. And that is radically changing the way that we as human beings work as individuals within the design and manufacturing process. And it's going to have a profound effect upon what we do within our profession. And there's an uncomfortable statistic behind that. This is a statistic that comes from the University of Oxford and Wharton Business School that says that within the next 20 years, 47% of tasks in the workforce today will be automated. And that's an uncomfortable statistic to face. But you really have two alternatives. You can either bury your head in the sand and hope that that doesn't happen and maybe hope it doesn't go away. It's unlikely that it's going to just go away. Or you can face that statistic and the value and the opportunity that it represents to redefine what people do in the business process. And as Andrew said on Tuesday, we know this will happen because we've seen it happen in other industries. We've seen it happen in the publishing industry. You know, for 200 or 300 years, not much happened since the advent of the printing press. And then along comes Adobe, Microsoft, and Apple, and they redefine that industry with desktop publishing. You all remember the what you see is what you get. That's familiar to everyone from back in the 90s, and it totally redefined publishing. I remember back in the UK, there's a place in London called Fleet Street where all of the country's papers were produced every morning, and it employed maybe 80,000 people. And within the space of 18 months, that drastically changed. Virtually nobody was employed there anymore. Now, that's a hard fact to face, but over the next decade, there were millions of jobs created in an extended economy of digital publishers and illustrators, jobs that never existed before. So this represents massive opportunity, and we see the same thing happening in manufacturing. And that's what Andrew referred to as desktop or push-button manufacturing. Now, to embrace push-button manufacturing, we believe you need something radically different in the way that you design. And that is what Fusion 360 is all about. It's the convergence of design and manufacturing that Lisa spoke about earlier. And what we want to do this morning is provide you with a few exciting announcements about how we're developing and evolving that platform to help you become even more productive and innovative. And to do that, I want to go back to Modbot. Now, you remember I talked about Modbot at the beginning of the presentation. This is Adam. And Adam is now stood in front of not his prototype, but his full production modular 6-axis robot. And the reason I wanted to show you this is that Adam's just closed 2 deals, one with Boeing and one with Siemens. Now, imagine that. Robotics is an incredibly difficult industry to enter with very traditionally high barriers to entry. Adam and his small team of engineers have been able to win contracts and orders with 2 of the biggest manufacturers in the world. And that represents the type of opportunity that Andrew was speaking about for more and more people to embrace this type of automation and technology and create new jobs that never existed before in the past. But Adam faces some challenges as a design engineer and his team of engineers when they come to integrate that product development process together. They need to stay continually ahead of the competition. They need to be constantly innovating. Now, I'm going to show you a couple of announcements here that will help them do that. The first is a technology called AnyCAD. You may remember that we introduced AnyCAD to Inventor some time ago. We've now introduced AnyCAD to Fusion. What that means is that as an organization, you can now start to use both of those technologies together. And I wanted to give you a quick example of what sort of benefit that might deliver. So in this example, we're going to use one of Adam's modbots as a production engineer working on the manufacture of a CubeSat. So as you can see, this is the robot that Adam and his team have produced. But working in our organization, we're using Inventor to design and develop our CubeSats. So the Inventor engineering team is building up the CubeSat directly inside of Inventor, as they would usually. They're fully detailing that design, and then they're sharing it with their production engineering department using Fusion Drive. That enables the production engineers to open that data directly, not translate it, but directly open it. They can even take SolidWorks information and embed that here as well. They can start to federate data together. And having acquired that engineering data, they can now use it to modify the soft jaws on their robot. They're going to perform a Boolean subtraction so that those soft jaws match the CubeSat for a pick-and-place operation. But they're also going to test it out, because don't forget, Fusion also has access to things like nonlinear simulation. So in the operation and sequencing of that pick-and-place operation, they can test not one, but 20 different FEA studies, because they can use the power of the cloud to parallel compute. And in this example, they can see that the uprights on the CubeSat aren't strong enough to withstand some of the loading conditions. They can communicate that back to the engineering department, who reopen the design in Inventor, replace the uprights now with solid hexagonal bar. But because the AnyCAD association keeps the associativity between the products, now the uprights update automatically, and so does the Boolean operation that defines the soft jaws for the robot gripper. So it really does mean that a change made anywhere is now reflected everywhere, not just in the part models, in the assemblies, and in the 2D documentation that's shared with the shop floor, but also across any simulation studies that are being produced, or any manufacturing NC code that's being created to drive the CNC cutters on the shop floor. As I said, the change made anywhere is now reflected everywhere across the entire design and manufacturing process, thanks to AnyCAD. But remember that Adam's team is more than just mechanical engineers. They combine 6 different engineering disciplines together. One of those engineering disciplines is electronics. So I'm also pleased to announce this morning the introduction of SPICE simulation within our electronics environment. So in this example, what we're going to do is take one of the arms from the robot, and we're going to start to define the footprint for the PCB board. So we can use the mechanical environment to start to lay out the PCB footprint. And having done that, we can take that information directly into our electronics environment. And in the electronics environment, we can now use that SPICE simulation to understand whether we're going to introduce any interference between wiring in the schematic. So we can start to evaluate the performance. And having evaluated it, we can then use the footprint to lay out the componentry, route all of the traces together, and then reflect that back in the mechanical environment. Now you can see as the robot rotates, we're also going to have to create a clearance for wiring. But again, because there's full association, we can communicate that back to the electrical engineers. The update remains associative. We reroute all of the traces and reflect that back on the board, which we can then use for thermal simulation. So now we can look at the heat dissipation across that board. And here's the first engineering challenge that Adam and his team have got, because believe it or not, these robots create a tremendous amount of heat. They need to dissipate that heat. They need to be able to dissipate it effectively like a heat sink, but remember, a heat sink has the luxury of always being static, and heat always rises. These robots aren't always static, they move around. That's a generative engineering problem right there. The second issue that they've got is that for every gram of weight in one of those modules from the robot, it equates to 6 times that weight for lift capacity at full extension. Now what that means is that every gram of weight you strip out from one module, you can lift 6 grams more at full extension. And that is competitive differentiation. Because if you can remove half a key here, you can drastically increase the amount of weight you can lift, and you can move your robot into the next category of robots. And if you're selling your robot for $15,000 and you can move into the $100,000 category, you have a significant competitive advantage over everyone else in the market. So we're providing the tools and technologies to enable Adam and his team to do exactly that. Remember Woody. Here is the example of Woody. Parametrics are still great for defining things like the interfaces. So we still do that using parametric systems. But we blend that seamlessly with things like T-splines to do some light industrial design and styling. We're also going to create an air pocket, an opening. But we're not going to leave that open because someone could put their hand in there. It would cause a problem. So what we're going to do is lattice it. And we're going to use our latticing study to understand thermal dissipation. Now remember, there is no cost for the complexity because we're going to print this. So by latticing it, we're solving the problem of how we dissipate heat effectively, and we're removing weight, creating 6 times the lift capacity. We'll then pack it along with the CubeSat, and then because there's no such thing as additive manufacturing without subtractive finishing, we'll move back into Fusion's machining environment and start to use some 4-axis machining and 5-axis finishing here around the lightning holes. That creates not the robot of today, but the robot of tomorrow by embracing design, automation, and manufacturing technologies in a way that no one else is doing. And it's not science fiction. It's real-life product. You can see it right here. If you get a chance after, maybe come take a look at it. This is a print from titanium. It took us about 2.5 days to get this back from Germany, which shows some of the digital connectivity across the supply chain that we're talking about. This radically changes what's possible in the market. If you're not exploring this technology, you're putting yourself and your company in jeopardy of being disadvantaged by the competition. So you might ask yourself, is Fusion a CAD system? Is it a CAE tool or a CAM tool? Does it do data management? And as you can see, the answer to all of those questions is no. It's not one of those things, it's all those things. It's a next-generation product development pipeline, and it's built to unlock that creative freedom that Lisa spoke about this morning. But building a digital pipeline that's connected is only half of the solution. Once you've connected the pipeline, you have to think about how you automate that process. And that's where generative design and manufacturing steps in. Now, you've seen a little bit of the latticing technology that we showed you there for optimization. But in this example, I want to talk to you about full generative design and manufacturing. And what I'm super excited to announce this morning is that Autodesk's generative design service will now be available to Fusion Ultimate customers. So the technology that I'm showing you is not research technology that you saw from Airbus. What we've done is we've taken that research technology and we've packaged it and we've made it available through your subscription to Fusion Ultimate. So let me show you an example of why that's important. And there really is no better example than Lightning motorcycles. These guys make the fastest motorbike in the world, with no exception. It does 222 miles an hour, and it has an electric powertrain. It's a one-of-a-kind bike. There is nothing else like it in the market. It's a winner, and it's great being a winner. The trouble is, when you're a winner, you want to stay being a winner. And that's where you need to use this automation technology to stay ahead of the competition. So let me show you what that means. So again, let's step back to Fusion. Here you can see the Lightning motorcycle in the Fusion environment. It has a traditional swing arm on the rear of the bike. But what we're going to do is use the Autodesk Generative Design Service to drastically change the way that we manufacture this. So we're going to specify where the mating points are in the assembly. We're also going to specify the manufacturing processes that we can use. So this isn't topology optimization. We're looking at the manufacturing processes, the loading conditions, the materials we want to use, because there isn't one right answer. There are many, many different design alternatives that we could select. And here what you see is the tool that you now have access to that allows you to browse that solution domain, productized for anyone that owns NetFab or Fusion Ultimate. And what that means is you can start to refine the design. You can start to pull those stats in so that you can look for a particular iteration that suits your specific market requirements. And once you've selected that, of course, you can still use all of the traditional tools like the nonlinear analysis just to check as a final check before you move into production. But of course, this needs to be additively manufactured. So we'll specify the build envelope. We'll also specify the support structures. But what we're also going to do is connect to NetFab. And we're going to do that by specifying the machine tool we'll use to laser sinter this powder, the material that we'll use, because then we can simulate the build process itself. And the important thing about doing that is we can understand whether we're introducing any shrinkage or warpage as part of the additive process. But of course, there's no such thing as additive manufacturing without subtractive finishing. So understanding where there might be shrinkage or warpage means that we can go back to the subtractive environment and start to do some adaptive tool pathing to clean up the finished geometry and arrive at a new generative design that's never been seen before until today. And you can see this right up here with me on the stage today. And this is pretty amazing technology, right? I don't think I've ever seen anything like this, and I think you're going to see more of this. And you're going to remember back to this presentation in 10 years' time, and you'll go, yeah, I remember when that crazy English guy was talking about this stuff. And you'll see more and more of it out in the market, because this technology is now becoming accessible. In fact, every one of you in the room now has access to it if you want to start to embrace this as part of your design and manufacturing process. It's radically changing what's possible by a human being to develop as a product, manufacture, and take to market. But it doesn't stop there. There's another announcement. So it's one thing to fully automate the design and manufacturing process, but you also need to be able to connect to the physical production of that product itself. Remember back in my theoretical part of the presentation where we looked at machineering simulation, the virtual commissioning of the factory? You can't do that virtual commissioning unless you're starting to capture information from the shop floor. So my fourth announcement this morning is that we're launching a brand new product called Fusion Production. Now, Fusion Production means that you can start to take the information you define as part of the design and production engineering process and provide people on the shop floor with access to that data. You can close the loop from the production environment. This is KMP. KMP are a Fusion 360 customer. They use Fusion 360 to develop powertrains for sports vehicles. Now, KMP, they design, they embrace much of what I've shown you from the Modbot example as part of their product development process, but they're also working with Fusion Production. And what that means is that as they've designed and engineered the product, they've also gone through the production engineering process of developing the CNC machining strategies. And those strategies can be directly connected to Fusion Production. That means that you can use the sequence of setup and tooling to define your methods of operation. That means as the production engineer, you're directly connecting the design and manufacturing environment to the shop floor that physically produces those products. You can even schedule the job as a hot job if you need to push it through production quickly. And operators on the shop floor can get access to that information with a mobile device. So they're not tethered to a computer. This runs in the cloud. That means anyone, anywhere across the supply chain can then interface with this. You get line of sight for the physical production of your product anywhere in the supply chain. You can even resequence jobs if you need to rush a job through a particular machine tool to meet a customer contract. And the machine operators can provide feedback back to the production engineers and the mechanical designers directly from the shop floor so that you're closing the loop on quality issues. We even connect to the machine tools themselves to get utilization statistics. So we can look at machine utilization and understand the down and up time. We can optimize our production environment for greater efficiency and throughput. So this represents a huge leap forward for Fusion and connects the design and production engineering environment to the physical manufacture of the product. Now, of course, we want to make as much of this technology accessible to as many of you as possible. And that's why we've expanded what was previously the product design collection. Because we don't believe fundamentally that you can anymore separate design from manufacturing. The two are intrinsically linked. And any of you that are on subscription with the collection, we wanted to make that technology available to you, not just through Fusion, but also through Inventor as well. So for my final set of announcements this morning, I want to turn to an Inventor customer called Radical Transport. And Radical Transport make these high-end hoverboards. And they're currently working with Inventor. So in their production engineering, in their digital engineering department, they're using Inventor to define all of their parametric designs. Now, of course, Inventor provides them with a high degree of sophistication to develop those products, but they would only be getting a small return on their investment if they didn't extend those digital assets across the rest of their business. So whilst this might represent great productivity in the drawing office, to get a true return on investment, you need to start thinking about things like the operational performance of the product. So when a rider rides this board, loads don't stay static, they move dynamically. That is nonlinear simulation. So what we've done with the product design and manufacturing collection is include NASTran, nonlinear simulation, directly inside of the Inventor environment. But of course, all that information is managed by Vault. So what we've also done is we've connected Vault to Fusion. So you can selectively take a project or a folder or a set of documents from Vault and publish them to Fusion, connect them. That means you can combine that AnyCAD technology that I showed you earlier with any data. You can start to connect the two together so that when you release a product to manufacturing, those production engineers at the CubeSat factory can now open that data up in Fusion, and they can start to use it to collaborate or perform downstream operations as one single team where all the updates between the technologies flow without any issue. We've also introduced the same 5-axis machining directly inside of the Inventor environment because we don't believe in holding any of this technology back from any of our customers. On top of that, we recognize the fact that many Inventor customers use a lot of sheet metal. And of course, 5-axis subtractive machining is only one part of the manufacturing process. So my final announcement this morning is that we're pleased to introduce the inclusion of nesting directly inside of Inventor. So when you've developed it's obviously a good one to finish on. So when you've defined the flat pattern blanks for your sheet metal, you can nest them based on material types, get maximum sheet utilization down on the shop floor. But remember, it is a completely unified design and manufacturing process, which also lets you create the NC instructions for driving the router or the laser profiler. So you have a complete design and manufacturing solution. So we started this session by explaining why automation is good for all of us and how it unlocks the creative potential, freeing all of us to do more. But we've gone one stage further. We've shown you with the tools and technologies that I've illustrated this morning that automation represents tremendous opportunity for all of us. We've shown you the convergence of design and manufacture and its power to automate the product development process in a single product development pipeline. It's complete, it's connected, and it's instant on. With your subscription, every one of you in the room has access to the future of making things. And it really does enable any one of us, anywhere in the world, to make anything. So, thank you for being a great audience. I hope you have had a fantastic Autodesk University 2017. Have a great afternoon, and I'll look forward to seeing you back again here next year. Thank you.